All right. So, yeah, it's me. Welcome, everyone. And first of all, thank you for coming because there is a lot of interesting sessions in parallel from really good speakers. But first of all, thank you for coming and showing your willingness to learn something new about future protocols and in some interesting way. So, my name is Oleh. I'm from Ukraine, from Kyiv, so I can understand a little bit of Polish, but not of all of those. I work for Netify. I'm doing lots of reactive streams and reactive programming nowadays. I'm working on protocol RSocket itself, so I'm part of core team. I did contribution to Project Reactor and trying to popularize that technology, and wrote a book about reactive programming. So I have some knowledge in reactive programming and reactive streams. And basically, yeah, this is my book and a little bit of marketing. I'm gonna give away a copy of this book for one of the most active attendee for this session. So pay attention about how you can win this. All right, a little bit about the main part of our session. So the agenda, what are we going to talk today? First of all, we have to understand what kind of problem do we have today. This talk won't be about writing multiplayer core logic or something like that. We are not going into like how to build UI or this and that stuff, like the logic thing. But we are going a little bit beyond this problem. We are going to look what kind of problem we have all today. Because today we are building microservices. I'm curious, how many of you are building microservices today or distributed system? Really, just a couple of? I'm pretty sure that every one of you are building either like plain web application or a little bit more than just plain web application. So today we are building distributed system. And today's the main problem is how to properly connect all of them, how to make the communication smooth, really fast and efficient. Even though you're going to build really efficient algorithm inside your computers, inside your program, the bottleneck will be your communication. That's kind of problem we are facing today. So today we are going to talk about protocols. And we are going to compare different protocols in order to see which one is the most efficient protocols for doing cloud-native applications. And in order to make this comparison a little bit more fun and like more engaging, we are going to compare all of those protocols in real-time multiplayer game like Pac-Man. And we are going to have fun by playing this Pac-Man game and feeling whether this protocol is better than that one. This is what we are going to do. And afterwards, we are going to define the best one. All of you will be playing and will be seeing what is the game experience, what is the latency and so forth and so on in playing this game. And after all, you all will define the best protocol. Does it sound good for you? All right, perfect. So let's start with multiplayer requirements, or what do we need to build or what do we need to have in our multiplayer Pac-Man game. First of all, in order to build multiplayer game, we need something to share, like web server. So we have web server, and the simplest way to build multiplayer game is to share it over the browser or like Chrome, whatever browser we have today, so web application. And any web application means that we send request and we return and we receive like index HTML page. But nowadays you want to build something like cutting edge, so we expect that all required things will be pushed from the server side to our client without any additional requirements, right? That's what we want to have. Afterwards, we want to make some first interaction, like we want to send, who am I? I'm Oleh, I want to start playing, and I want to receive the state of the game in order to understand who is playing at the map, or who is at this point in time, what is the state of the game. Afterwards, I want to start like doing some actions. So basically, I want to move and I want to update somehow the location. The simplest way to share my location is basically the dummiest way, is to say, all right, I'm here, I'm here, I'm here, I'm here. So that's what my application is doing right now. It's sending all the stream of location updates on every movement of the Pac-Man. At the same time, it receives the same stream of updates from the server side in order to update. And in this way, we are doing kind of real-time multiplayer gaming. So we're receiving the stream of updates of all the players and move all of them. Finally, in order to make this game a little bit more interactive, engaging, competitive, we want to have some scoreboard, of course, and we want to like earn some points for eating, for example, food, or for eating Pac-Man by Ghost. And that would be the main challenge for you. You will be playing, and you would need to collect as much point as possible in order to be the best player. And in this way, the best player in this game will win the book. All right, this sounds really simple, right? Nothing really complex. So the main question which should pop up in your mind, where is distributed system here? Where is kind of all of those cloud-native challenges that I mentioned today? Basically, nowhere. It's just plain web application. That's why in order to make this application distributed, we are going to add a little bit of bloody enterprise, like some trendy words like Kafka, machine learning, artificial intelligence. So we are going to build a small business on top of that. And the business will earn from spying all of the players and learning how do they play. So basically, all the players will be sending all the important information to Kafka. So in any unclear case, if you don't know what to do, just put Kafka in between, and that will be a solution. So we are doing the same because Kafka is basically a real good streaming solution, and it's basically elastic storage, so we can just push data without carrying how many elements or messages we are going to send from how many clients. And Kafka will handle that. And behind the Kafka, we have our machine learning pipeline. We have like just a couple of machines and like virtual pods and whatever things, which lets us run our services. And then using all of those limited resources, we will try to process all of those data, collect and aggregate the information, and then finally to send all of this information to final pipeline to final service in order to somehow educate our bots or our machine learning algorithm or models in order to sell them afterwards. So the point here is this part of the system is distributed one, right? And the point about the thing about distributed system is that they're unpredictable. We don't know at which point in time our service is good. Like, we can know, but it could change suddenly without any significant notifications. So what could happen is that our machine learning algorithm or our server could start working really slow, and we have to be prepared to that, and we have to somehow control the flow of messages and say, right, we are not ready to receive. So in that way, we have to preserve the stability of the system. That's what we have to ensure in our application. So to quickly summarize, we have a couple of different communication from protocol perspective. We have server-side push, request response, client-side streaming in order to send location updates. We have server-side streaming in order to receive updates. And a part of that, we have some machine learning pipeline which should bring money to our business. So we have to make sure that it works stably, even though it works slow or fast in some unpredictable fashion. Is it clear what we have to do? All right. I started with something, as I said. I have already built something using, for example, Spring. How many Spring developers do we have here? All right, then this code will be familiar a little bit for you. I'm using Project Reactor. Any REACTIVE-STREAMS guru or fans here, fellows? All right, just one hand. Nobody heard about reactive programming before? Really? I'm pretty sure all of you heard. So Project Reactor is one of those reactive programming libraries, and I really like it because it lets you write really transparent and clear code and keep your application really fast in processing all of your messages. And part of that, I'm using really efficient protocol for message protocol for doing communication, like protocol buffer. Have you ever heard about protocol buffer before? All right, for those who have never heard about protocol buffer is message format like JSON, like XML, but it's binary message format. It's really small, so you can send as many as possible messages with the fastest speed, without network limitation. At the same time, on the front-end side, I'm using Phaser, I'm using Reactor.js for the same reason, and protobuf in order to have balance here and there. And yeah. I started with alt HTTP. You may wonder why. Basically, HTTP is plain and simple, right? We are using this kind of technique or this kind of protocol for many, many years. And if you're going to try to build something with Spring Framework, what would you have to do is basically add a couple of controllers, add a couple of annotations, and magic going to happen. That's what you have to do in order to build your HTTP API using Sprint Framework. That's really easy. But the question is whether it's fast, because we need low latency and we need high performance in order to make real-time game. So let's try to figure out first whether it's something, whether it works or not, and whether it's fast or not. Let's do that together. So please take your phone, scan this QR code, or just follow this link, and we're going to try to play this game together in order to figure out whether it's fast or not that fast. All right, so let me put this link. You will see the similar page. What you would need to do, you have to just put your name in the field, play start, and here we go. We can see some players there. So let me try to find someone. So yeah, it works. First of all, is it fast for you? Like, is it lagging a little bit or it's not lagging? Oh, I was written by someone. So let me expand it and see whether it's, for some reason, it's just stopped. A little bit shaky. Do you see that? Like, a little bit shaky. Do you feel the same game experience? Lagging, shaking, dropping messages? Any feedback, guys? I need you. Is it good for you? Is it bad for you? Is it not that well? It's not that well, right? Yeah, a bit laggy. So because of HTTP, if we're gonna look at that, we're just sending lots of messages, like in separate like requests, and we are dropping lots of messages, and so forth and so on. Yeah, I have to enable warning level in order to show you that we are dropping lots of messages, basically. That's why we are lagging, because we are not able to deliver all of them. So because of that, we experience some lag, some shaking, and so forth and so on. And in order to summarize what we saw, I'm gonna do that in one slide. Basically, why not HTTP? Because everything that we send is in a text format. It's text protocol. It's text message or text-based protocol. Sometimes it creates one connection. Sometimes it creates more than one connection. Depends on the version of the HTTP protocol. But in general, it use not a single connection. It overuse a couple of more connections, and our server have to deal with more than one connection. So it's more work for our application. So it leads to slow performance, to all of those lagging and latency. And a part of that, there is some communication rigidity, which means that the only type of communication we have with HTTP is request-response. Right? Nothing has changed from the protocol perspective. We can send request and receive response. Of course, there is some technique like server-sent event. How many of you heard about server-sent event before? Right, just a couple of hands. Nobody heard about that kind of streaming. There is a way to stream of messages from server side, like stream of text messages. But again, this is some hacky solution and nobody uses this today. And finally, there is a lack of resilience. You may wonder, what does it mean, lack of resilience? Basically, in order to understand what does it mean, you have to just look at this photo. It means that on the right side is your server, where on the left side is your client. We just send in messages. And in order to keep working, you have to apply lots of different techniques and libraries. You may wonder again, why? Basically, here is our server, here is our client. Here is our client, here is our server. Our client sends messages, send, and if there is lots of messages, like really huge stream of messages, our server have to store them somewhere, for example, in memory. So at some point in time, you get too many messages, and we start dropping them. Which one of the problems? If the messages are really important, we would have to somehow deal with them, and at some point in time, our server gonna crash, because we will store all of them without any kind of back pressure or flow control. So what do we need? Basically, we need back pressure. How many of you heard before about back pressure? All right, great. Just more than REACTIVE-STREAMS guru, but anyways, it's better. So for those who have never heard what back pressure is, basically back pressure is a way to say how many messages you are ready to receive before clients start to send in anything. So basically, what you have to say, what this kind of mechanism proposes you, is that the server or recipient or subscriber says, all right, I'm ready to receive 5 messages. So it sends this request, and in order to, like, as a response to this action, to this message, client starts sending like exactly 5 messages. They delivered, and then server are able to say, all right, I'm ready to receive more, asynchronously without any blocking. So in that kind of communication, server controls all the flow of messages from the client side. Is it clear? So there is a specification for that, like all of those cool things are implemented in REACTIVE-STREAMS specification. And basically what you have to know about like Java side is that there is publisher, subscriber, and subscription. And the way subscriber controls all of this flow of messages from the publisher side is over subscription request. That's how it works in Java, and that's how it works in Project Reactor, for example. So basically, it's clear that HTTP doesn't work for us, so we have to figure out what kind of protocols do we have from other what other protocols do we have today? HTTP doesn't work, so maybe HTTP2, a single connection, binary messages, so should be better, right? A part of that, we have WebSocket. That's really like not WebSocket, but TCP. But yeah, we have browser, so basically WebSocket. We are not able to use just a plain TCP on the browser side. So WebSocket is another solution which is fast. And basically, yeah, we have some protocols like Quick, other protocols like UDP, but basically they don't work on all of the layers, like in the browser, on the server side really well. And some of them are in development still, like Quick. So we are going to stick to those two. Does it make sense, right? So let's start with some comparison of them, and let's wonder how to compare all of those protocols. From my point of view, we have to first of all take a look at maintainability. What does it mean? Maintainability means that it's easy to develop this particular protocol or this particular framework. We are not spending lots of money and time just investing how to work with particular solution, developing some proof of concept and so forth and so on. We are able to Google and find an answer for a particular error or like problem that we faced. That's about maintainability. So that's how easy we are able to work with particular solution. A part of that, we really need stability for our machine learning pipeline. So we have to make sure that our stuff just works, and protocol should help us to do that really smoothly. And finally, for our case, we need something for high performance. So protocol should let us work really with low latency, with high throughput, so with high performance. And now let's try to compare them. So we have WebSocket and HTTP. Let's start with WebSocket, and let's ask ourselves why WebSocket, basically. First of all, because WebSocket is almost the same TCP, no overhead, just one additional kind of part of bytes in the frame related to frame size, and that's it. So it leads to high performance, a single connection which lets us multiplex everything that we want. However, on the other hand, why not WebSocket? From my point of view, WebSocket is a little bit complex in development. If we are going to talk about just plain WebSocket connection, which give us just stream of bytes and nothing more, it means that we have to develop our own protocol, we have to develop our message format, our message kind of size and framing, and basically it will end up with another application protocol which would have to be maintained and developed by us, right? That's something we don't want to have. We don't want to develop something new and reinvent another protocol just for our solution in our company. Of course, there is some existing solution. For example, like SocksJS and STOM. This is really one of the popular protocols, but in JS world, unfortunately. There is Socket.io, the same situation, and probably we can start looking into that, working with those protocols. But STOM, the STOM is as a protocol were developed maybe 10 years ago, and the latest update for Java server and client were maybe 5 years ago. Like the latest solution you can find, or the freshest solution you can find, is dated like 2015, which is not good. Socket.io is better, but anyway, why not all of those protocols? First of all, because all of them is just a pub sub. They give you streaming, they give you some API and ability to build routing and so forth and so on, but they are developed on top of publish-subscriber. So it's on top of just one communication model, just a stream of messages, which is not good for enterprise solution when we have to send request response sometime. There is no integration with Spring. You won't find any of those protocols well integrated with Spring, especially if you're trying to find something built on top of NetT, on top of really high performance frameworks, then you won't see any solution which is well integrated with Spring. And finally, all of those, like all of existing implementation in Java are too low level or too complex. You can find NetT STOM, but probably you won't gonna work with that on all of the levels for your enterprise application, because you would need to deal with these low-level NetT things which are really complex. I'm just wondering, how many of you tries to work with NetT before? 5 hands. So it's hard. That's why that many people we have. That not many people we have today with like as NetT developers. So it's clear that we need some good framework for building our things, right? And maybe you know some frameworks which gives us well integration like API, maybe integration with protobuf, some streaming, request response things. Have you ever heard about something like that? No? I'm gonna try to help you. Maybe you heard about gRPC. Have you ever heard about gRPC before? A couple of hands. So for those who have never heard about gRPC, basically why gRPC could be a good solution for us. First of all, it's built on top of HTTP2, which means all of this binary framing, one connection with all of those stream multiplexing are there. A part of that, like if you're gonna Google what Google says about gRPC performance, you will find that Google says that it's really good. So Google RPC is really good in terms of performance. Part of that, it has really good integration with protobuf, which means that all you have to do with protobuf, basically you have to define all of those proto files. You have this kind of definition of services and API and communication model, so you can say this is service A and this is service B, and my service A has like start method, which is request response, which is clear. There is no string in words. And there is another service which can say, right, this is streaming from the client side and this is streaming from the server side. So all of those communication types are built into protobuf, and you can use it in order to build your API for gRPC. And you don't have to develop anything on yourself, like writing some classes and so forth and so on and doing integration with gRPC. All you have to do is to use one generator, one like Gradle or Maven plugin in order to generate all the stops and then build your business logic like that and integrate it with Spring in one annotation. So basically, it gives perfect integration, and a part of that, it gives you really good stability, as Google says. Or I'm just addressing all of the things to Google. So if you Google again for gRPC reliability, you will find that gRPC is reliable. And it means that it's something that we can use, right? So let's try it. Let's try to play with gRPC Pac-Man and see whether it's faster, reliable, and best solution. Let's see that. I don't know, but we will figure out together. So the same link. Let's follow this link. And again, we are playing. Okay. So any feedback so far? Still a little bit lagging. At least I'm not able to catch this Pac-Man. A little bit still shaking. Is it lagging for you as well? A little. Yeah, it's a little bit better, but still lagging, right? Still shaking. It's still not the best performance as we wanted. So you may wonder, what's wrong with gRPC? Why it's still lagging even though they say that we are using one HTTP2 connection and so forth and so on. So basically, in order to figure out what's wrong with gRPC and with our Pac-Man, you have to basically go to console open your development console, see what network sends from your client to server, and you will see that for some reason, it's the same HTTP1. Again, HTTP1, why not HTTP2? What's wrong? So if you're gonna look and Google for what's wrong with gRPC again, maybe this kind of query will be better. You will find that gRPC architecture and gRPC-WEB works like that, which means that for some reason there is something like gRPC-WEB proxy, and all of the communication is happening with HTTP1 and HTTP2. So what does it mean? It means that in order to let gRPC-WEB work, so gRPC for web, you have to install an additional proxy like Envoy proxy. And there is no guarantee that basically you will upgrade to HTTP2 because there could be another proxy and there could be like routers and so forth and so on. And what it leads to that you have to work with HTTP1 again, and then you have to open connections again and again in order to send your like request response because HTTP2 didn't change protocol like specification. You have only request response from the browser side, nothing more. And in order to achieve streaming, you have to open a few more connections in order to achieve kind of server-side pushes. And that's how it works. It means that it's not efficient. But you may wonder again, but wait, what about backend? This is frontend, all right, we can use different solution like Socket.io and we can put Node.js in order to build our game logic, but we have backend, we have our machine learning pipeline. Maybe it will gonna work it will be better here, because on the server side, we can control everything. So, and again, gRPC says that they have back pressure, and if you're gonna look at implementation side for Java, for example, you will find out that there is subscriber API, and subscriber has this magic method request 5, which means that yes, we can control back pressure, we can specify how many messages do you want to get on the subscriber side, right? However, don't be fooled by Google and all of those Google developers, because first of all, you have to look at the same time on the publisher side, and the publisher side is really tricky. Do you see the problem here? Let me highlight this point a little bit, and the problem point. Basically, under the hood, you have volatile Boolean is ready. And what happens when you read volatile Boolean and then you try to do something? The racing can happen, right? And you can read that volatile Boolean is true, but at the next point, because of multi-threading and all of this Java stuff, is ready could be false, and you can send more messages. And actually, there is an issue on the GitHub account for gRPC and Java. And you can find that someone complains about gRPC back pressure and stability, and someone says that there is racing on this ready field, and the official maintainer says, right, there is this kind of issue. There is racing, and unfortunately, gRPC can nothing to do with that. The only guarantee that we can provide is that if you read is ready and is ready is false, there is no guarantee that your application has already observed it. So let's close Curtis and say, thanks Google for good RPC framework. And let's summarize. Basically, our publisher can oversend a couple of messages, so which is not a big problem. But what if we have not only single subscriber or publisher in our application? What if we have a little bit more, like 1,000 of publishers, which is running on the same platform or on the same Java application, and all of them can overproduce a couple of messages? So in order to understand the problem, we have to run a test on our machine learning pipeline. So basically, what we would try to do is to run really good machine first, like subscriber. This is subscriber in our pipeline. And then we'll try to suddenly decrease the stability of our system, of our subscriber, in order to figure out whether back pressure will be propagated through all the pipeline and our system will still be working afterwards. So we have to figure out whether this guy will survive or die. All right, if you're going to run this test, you will find all of those real, all right, so let's run it first. Run. Yeah, we are going to make it really big at the first point. Then we see that producers produce the same number of messages we consume. But then we suddenly decrease the speed. And what could happen is that because all of those kind of producers reading this is ready field, they still can produce more messages than we request. So we request one message, and they produce like 1,000 of them. That's a problem. And of course, after some period of time, the system will gonna stabilize. But in order to figure out the problem, we have to look on the graphs. So I've done some measurements, like throughput on the publisher and subscriber side. And in order to see this gap, like what happened when we applied back pressure, when our system became unstable, so in order to see the point, we have to highlight a little bit two graphs. This is a throughput of our publisher, and this is the throughput of our subscriber. And you can see there is a huge gap between them, which means that a few K of messages, like 20K of messages, were stored somewhere. And the question is where? Basically in memory, right? Everything which is not consumed are stored in memory. And this is like a snapshot or a picture of memory consumption, and you can see the spike of memory consumption. And it could be fine, like, all right, we have like 64 gigs of memory, which is good. But nowadays, we are living in cloud-native environment, so we are running everything in containers, in Kubernetes, and we are given just a couple of gigs of memory. And in this setup, it would lead to out of memory, which is something we don't want to have in production. So yeah, gRPC has back pressure, but it's not ready for production. All right, let's summarize. Everything is either slow or really hard in the implementation, from the implementation perspective, or doesn't work in browser. Back pressure is kind of something we still need to have in our apps. And the main question, whether we want to solve all of those problems. The same question were asked at Netflix 5 years ago. So I guess everyone heard what is Netflix, right? Yeah, we were watching, all of us were watching movies from Netflix. And Netflix basically is a huge shop of microservices, and this is a really great distributed system. And what they do, they basically have big server which they can control, which they can manage. And they have gateway which sends all of those streams to all of the application, or not application, but devices like mobile devices, PlayStation, and whatever. And at some point in time, they decided to use gRPC in order to utilize better their CPU, their computers, and their hardware. And they tried to apply gRPC and see whether back pressure could be propagated. But the problem is that they can't control this part, but they can't control all of those grainy devices, right? And everything can happen to those. So what happened to them is that at some point in time, all of those devices started lagging, the network became slow, and all of those messages stored at the gateway. And after some point in time, it just died with out of memory. That's what they observed during their experiments with gRPC. And you can find real interview with one of the ex-developers from Netflix Edge platform. This is basically the team which is working on all of the innovations. And this person says that, yeah, the gRPC didn't work for them. All right, so what Netflix did? Basically, Netflix is the team, the company which is doing really great innovations. They developed RxJava. They developed all of those cool technologies like circuit breaker and so forth and so on. So they decided to implement framework and protocol which has real back pressure, which solve all of their problems. And this protocol got named RSocket. So let's take a look at RSocket, and you may wonder what RSocket is. Basically, RSocket is a bright future as for me. I believe in that protocol. And in few words, RSocket is REACTIVE-STREAMS, so this specification as a network protocol. That's what RSocket is. And if you're gonna look at OSI level, so we have all of those different levels of like networking. There is transport layer and there is application layer. And RSocket takes only layer 5 and 6. So it let us design whatever we want. All right, let's take a look at RSocket performance and stability first, and then we will try to learn more about RSocket. So let me copy this link again, and let me merge those two screens in order to let you scan the QR code, and let's play into RSocket version of Pac-Man. And as you can see, it just smoothly works. Do you see that? Is it working really smooth for you? Much better, right? Stable connection, sending messages really fast. So you may wonder, how does it work then? So let me explain a little bit about RSocket, and let me educate you a little bit. So basically, RSocket took everything good from all of those network protocols that we had before. It's really binary protocol, but it's focused on real messages, on application messages. Because nowadays, we are not sending bytes, we are sending messages. So this protocol let you, for example, encode your Pac-Man into binary format and send it as a whole message. So as a recipient, you will be able to receive the same set of bytes, then decode them back to your messages without any problem and without any bytes counting on yourself. So it gives you like this binary messaging, application layer messaging. A part of that, it multiplex protocol, which means that all of those logical streams you have in your app will be multiplexed through one connection. And you don't have to work with that yourself. RSocket as a protocol provides like stream identification on the protocol level, and all you have to do is to use, for example, Project Reactor or RxJava or any reactive streams library like Akka streams in order to send your logical streams over the network. A part of that, the most powerful thing about RSocket is that like it takes only layer 5 and 6, which means that it can basically work on top of any lower layer protocols like TCP or WebSocket or, for example, Quick. It doesn't matter what would be the lower layer protocol. It just sends frames and that's it. So it could be even iron. Any protocol without changing your API. So what else? Reactive streams back pressure. So how does it work here? So basically, as I said, we have framing. And your request end method will be transformed to binary frame, will be sent over the network, and will be decoded back to the same method invocation, but on the different server. And your producer or publisher will be able to produce exactly the exact number of messages you requested, which is really cool. So we have real propagation, transparent propagation of back pressure over the network. And this protocol is really peer-to-peer. At the very beginning, we have client and server just only to establish a connection. But afterwards, they turn into peers, and both of them can request for some data. The client can be a server then, and the server can be a server then and client at the same time. And there is no separation between client and server anymore after the connection established, which is pretty cool. And finally, this protocol is not only about streaming. You saw the streaming part, but it's not only about streaming. Netflix thought about was thinking about all kind of communication patterns. And in protocol, we have request response, we have fire and forget, which is kind of upgraded version of request response. We have request stream in order to do proper streaming, and we have even bidirectional streaming. So we have all of this type of communication without any limitations. So some other notable features. Basically, circuit breaker, rate limiting were separate libraries before, but now they are built into the protocols, and you don't have to use separate libraries or external solution in order to ensure that your system works stably. Then it has resumability. Just imagine you're building mobile apps, and the problem with mobile phones is that network is unstable. You're connecting here with 3G, then you switch to Wi-Fi, and your stream of messages just dropped because you connected to a different socket, which means that you somehow have to restart the whole stream, and this is another challenge. This part is solved in the protocol itself, and it lets you resume your logical stream without losing anything. So this is one of the coolest part. And finally, there is fragmentation. So if you're sending gigs of messages over the wire, it lets you just split them on the smallest chunks without overwhelming the bandwidth of the network. All right, let me show you some code, and let me show you how to work with RSocket. For example, on the Java side. So basically, what you have to know about RSocket is that there is RSocket interface. That's the simplest. And RSocket interface gives you all of those communication patterns that I mentioned before. So basically, this is like a client and responder at the same time, because it lets you call something, and it lets implement like your API using all of those methods. Then what you have to remember and what you have to know about RSocket is that there is payload. And payload is basically a representation of your message, of your logical message. It gives you an access to the binary data, so you can send your message or JSON or whatever in binary format. And a part of that, it gives you something like metadata, so you can provide meta information along with your payload or with your main message. And you don't have to develop that yourself. This is built into the protocol, and you have to just use it. And there is much more cool feature related to metadata, because there is something like composite metadata, and you can provide routing, tracing, span, and metrics in the metadata without kind of reinventing your binary format for that. So in order to start building server, you have to use RSocket Factory. This is the start point for RSocket, and you can build client or connector and receiver. So in this case, we are interested in receiver because we want to build first the server, and then you have lots of different flags. You can enable resumability. This is optional part. It's not mandatory part. You can just enable resumability or disable it. Or, for example, you can say that under the hood, we are using netty in Java, which means we are using coolest part of netty like zero copying. We don't have to copy the binary data from network card to our heap, which leads to more GC cycle. We can directly access to out of heap memory and use that part of the memory without copying and without any garbage awareness. So we can specify that we want to use, for example, zero copy mechanism of message delivery. And there is lots of different things like leasing, and you can set up whatever you want. But at this point in time, we are interested in specifying like our handler. So we are saying, all right, let's define socket acceptor. And there is socket acceptor interface, which basically handle the connection and represent your connection as RSocket. So your RSocket and the client is, or who connected is RSocket. And basically, it leads to the ability to say, all right, I want to send something to someone who just connected to me. So it's basically peer-to-peer, as I said. And a part of that, client provides some connection setup, which means that you can verify who is connector, what it has, and all the rights of someone who just connected to your application, which is cool. Then you have to define, of course, some more feature. Let me just cheat a little bit. Let me define acceptor really quickly. So you can expose your API as an abstract RSocket, which is basically implementation of RSocket with all of the methods which returns error to your client. And then you can override, for example, request stream. And what you have to do, you have to operate with reactive streams, like this project reactor. And it gives, like, it's really powerful tool, so you can log, you can do whatever you want without any problem. So you can monitor your messages, you can build really cool stuff using project reactor. And this API is built into the library. And then you have to send like 100 of messages just in case, or 1,000 of messages. And basically, then we start our app. That's easy. Oh yeah, I forgot the important part. We have to specify transport. This is one of the builder important things. And you have to supply server transport, which is basically interface. And there is a couple of like TCP server transport, so you can use TCP, or you can use WebSocket, because you know that it's possible to do communication with browser, so let's accept WebSocket connection. And you can easily switch transport without rebuilding your app. So for example, let's expose WebSocket endpoint, and that's it. That's what we have to do in order to make our application running. Yeah, let's start it. And on the other hand, there is implementation in other languages, because this is just a protocol. So there is the same implementation in JavaScript, yeah, with a little bit different API, but basically here we can create our socket client, we can say, right, we want to connect to this endpoint. We can specify encoder of our messages here as well. And then we can specify MIME type for our data and metadata. So we can say, OK, this is JSON, this is like something else. There is no limitation for that. And there is something like heartbeat or heartbeat in the protocol, so you don't have to implement like ping-pong messages yourself in order to make sure that the connection is really alive. This is built in as well. And then connect, and you can request, like because this is our socket, so you can request for stream and receive some of the messages. So let's take a look. This application is running right now on the browser side. So let's open our browser really quickly. And here we go. We received a stream of messages. Do you see that? Like this, it says we connected because exactly the same we have here. So we log we connected, and then we log all of the received messages. So here we received 10 messages. But you may wonder why 10? We have thousands of the messages, right? Why 10? Basically because I applied back pressure. I said I wanted 10 messages, and I can change really this number. I can easily change this number to 5. And then, let's reload it. It takes a while. Here we go. I received 5 messages. I can control this number of messages as I want without any problems. And if we're going to look at the server side, I'm logging all of those actions on the server side. You will see that here we received request 5. Exactly the number we specified on the browser side. That's cool. And basically, this is real reactive streams, so we can easily say, OK, we want to cancel subscription, or we want to do whatever with our subscription we want without any problems. So we can receive some part of the messages and then cancel subscription, and then that will be propagated as a frame to our application. And a part of that, as I said, we can build real peer-to-peer communication. So you can imagine that we want to kind of let our browser mine Bitcoin for us. You can cheat your clients, and you can use their computers to mine Bitcoin for you. So you can do that really easy. You can say, all right, let's define, for example, responder. We can do that on the JavaScript side as well, on the client side as well. And we say, all right, if client going to ask us for some Bitcoin, we are going to mine them, right? We have to specify that this is any, basically. And we got payload, and we say, OK, I'm going to mine something for you. And on the clients, on the server side, we can use, this is a chapter. So we can use Bitcoin algorithm or request, Bitcoin request on the client, on the server side in order to say, please, client, mine some Bitcoin for us. And we can just restart our app, and we will see an additional message from the server which asks browser to mine Bitcoins. So isn't that cool? We can mine Bitcoin from our browsers. That's perfect. And here we go. Where is that? It's not ready. Where is that? Yeah, we got this message. Please mine Bitcoin. Do you see that? Perfect. And on the browser side, on the server side, we see that, yeah, I'm going to mine some for you. Great. I like it. All right. Let's go back to slides, and let me finalize all the things. So you may wonder, what about real API? Because by that point, we just got 4 methods, like request, respond, request, stream. But at some point in time, we would need to build real application with all of this huge API, enterprise API. Basically, there is integration with RPC. And if you want to use RPC, like protobuf RPC, it's possible. There is the same plugin. There is the same core library like RSocket RPC, which is a replacement for your Google RPC. And you can generate all these stubs in the same way, using the same set of plugins without changing anything. And you will get the same set of interfaces and stubs. Perfect. Or if you don't like RPC, if you're a fan of Spring, like Spring Messages or Spring Web Flags, you can easily use Spring feature with RSocket. There is Spring Boot RSocket Starter, which lets you define, for example, something like this, port and type of communication or transport. And then you can define your controller in the same way with the same set of annotations, and magic gonna happen. This is perfect, like, development experience. I really like it. It provides everything you need. And in general, to summarize, it has everything for you. It has different clients, like in different languages. It lets you use any kind of architecture for highest level of your OSI model, any message format, and any transport. So really carte blanche for you. So what about stress test and stability? It has real back pressure, which means that you have to propagate like real request and message from your server side or subscriber side to your producer side, and they will start produce messages only after they receive this request n. And if something went wrong, your client will have to do some stuff, and nobody will produce anything. And once like it's gonna be better, it will start like requesting but lower number of messages, and you will get stable system. So basically, the snapshot of or graphs from like throughput graphs from RSocket stability on subscriber and producer side looks really similar because there is real back pressure propagation. So you won't get any problems with this type of protocol. So finally, what are the advantages of RSocket? Basically, simplicity in development, really efficient resource usage, one connection for everything. High performance, you just noticed that playing Pac-Man. High flexibility in terms of communication model, and real stability because of back pressure propagation. However, you have to know about disadvantages because you will start working with that, and you will find that there is no documentation, for example, because protocol is still under development, and this is something not good. Because we are doing our best to make it more stable and more future ready, but we are still developing something. And a part of that, there is narrow adoption, which means that there is not that many companies which is using RSocket nowadays. However, those who are using protocol today are really great company. Netflix, Facebook are doing RSocket with CPP. We are doing some stuff with RSocket. There is Pivotal, and there is Alibaba, who is planning to adopt RSocket for IoT communication, which is great. And we have Reactive Foundation, which let us make our community bigger, which is perfect. All right, so to summarize the whole picture, it looks something like that. But in general, every protocol has its good side, and it provides some benefits for you. For example, Socket.io works really well in JavaScript world, and gRPC has really good performance with some type of communication. However, in order to build really stable and reliable system, you have to use proper protocol like RSocket. All right, what else? What do you have to do afterwards? Basically, you have to follow me. Yeah, that's you have to do. And there is a couple of useful resources. If you want to ask something about RSocket, there is community forum. You can ask anything you want, and you will get some support with RSocket. There is video channels. You may learn more about RSocket from other speakers. There is RSocket in Sprint, so you can take a look how RSocket works under Sprint messaging. And there is cloud-native implementation of RSocket, so you can take a look at this project as well. So that's basically all from my side. It's prize time, so let me find who is the most active attendee at this room. And this is someone with the name M, whoever. But thank you for your attention, and Mr. M, please come to me. All right, thank you. That's all.